Hello friends, my name is Vivek Sharma. Today we can cover this interesting problem that's called path sum. So in this problem we have been given a binary tree and a sum, and we need to determine if the tree has a root to leaf path such that the adding up all the values along the path equals to the given sum. So that's what we need to figure it out. And the definition of leaf node is a node which does not contain any children, right? So this is the diagram. It should not take much time to walk through this problem. So let's see, I just copied this diagram here on the whiteboard just to make our understanding what we are trying to do it here. So if I take pencil and if I start from this root node, that's called 5, right? So if we start from 5 and we need to add all the nodes till we find the sum, that is 22, right? So if we go left side, then basically first is 5 and then plus 4, right? And then you see the bold nodes, right? They are making the path and that equals to 22. So that's what I am just trying to accumulate here. So 5 4 9 9 plus 11 is 20, and 20 plus 2 is 22. So this is the valid path, and this should be the reply, right? So we should return true. So the output is boolean, right? And let's say, for example, if I am finding some path that's let's say 20, right? So let's try to again do the same thing. We will start from 5, we will do 4, and that is 5 plus 4 is 9, right? And 9 plus 11 is 20. So we find 20 till here, but the problem description itself says that we have to find a root to leaf path, right? So of course here the 11 is not a leaf, right? So 11, if 11 is not a leaf, then it means we should return false in this case, right? And we can take other examples also. Let's say, for example, we need to find the sum as a 23. We will start from again 5. We can take left or right, right? So let's see again the following the same 5 path. 5 plus 4 9 plus 11 is 20, and then this is 22 but not 23. And even if we add 11 plus 7, that is 18, right? So let's see on the right side, right? So if I choose the different color, maybe the red color, 5 plus 8 is 13, 13 plus 4 is 17, and 1 is 18, right? And if I select 8, 5 plus 8 13, 13 13 26. So this 23, even if we traverse all the path, we should not find any nodes that will accumulate as a 23, right? That will build the sum as a 23. So this is the problem. Now let's try to understand like how we can solve this problem, right? So let's go to the different page here. So first of all, because this is the tree problem, right, and we need to go to the, so there are a couple of observations here, right? And those couple of observations here is, number one observation is we need to go to from root to leaf, right? We need to find from root to leaf, and whenever we have to find from root to leaf, right, it means it looks like the pattern of the depth first search. And why I am saying depth first search, because in one direction we will go deep till the leaf, right? Leaf means if we find there is no children of one node, right? And then we will check, okay, if we will, the sum is equals to the given target or not, right? So sum is equals to, let's say in this example it's 22, right? So we will check, okay, if sum is equals to 22 or not, right? If sum is equals to 22, then we will say okay, then we will immediately return true, right? And let's say, for example, if sum does not equal to 22, then what we will do, we will again recurse back, right? We will just go back to the previous node, and then basically we will just traverse the other neighbors in the depth first manner, right? So here the intuition of the depth first is because it's saying that root to leaf. It's not saying that we have to check any label or anything else, right? So it's not breadth first, definitely it's a depth first. So we need to traverse in one direction, and we need to find if we can find that sum in one direction. If not, then we will recurse back we will come back from the leaf, and then we will just traverse another leaf, and even if there is nothing here, then we will traverse back again, and then basically we will traverse back again, we will traverse back again, and then we will explore the same thing on the right side till the leaf. We don't find anything, we will recurse back, and then we will recurse back, and then we will go explore the right side. So similarly we will just need to do basically in the depth first manner using recursion. So this is the one observation. Second observation is how we will find basically all this. So one way is basically we can just keep accumulating all the nodes basically. So 5 plus 4 plus 9 plus 11 and 22, right? So that's the one way that we can do. And once we can accumulate all this sum, and if it is equals to 22, then we can say okay, and then that is one criteria that it meets it is equal to 22, means the given target, and it is the leaf node. Then we can say okay, we can return true. If not, then we have to again traverse back, and then we have to make the decision based on the other searches as well, other direction. Means for example, if I don't find in the left branch, then I have to recurse back again, then go to the left side of the children as well, right? So another observation is here is the we need to have the all the nodes sum, basically this are equals to sum, all nodes add up to sum, right? So sorry, this is not too much readable, but what I mean to say is basically all nodes all nodes sum equals to given target, or let's say in this case 22, right? Just to simplify. So these are the two observations. Once we know these observations, let's create a couple of placeholders quickly, because we should not take a lot of time in this problem, right? So the base condition definitely is if root equals to null, then we are going to go ahead and return false. Why we are returning false? Because this is the base condition, right? We are assuming like once we will do the recursion, we want some base condition that will tell us okay, just stop here and then just revalidate again. So that's why this is the base condition, and we don't want to assume and just think in a very first step, right? So sum equals to 22, and let's say root is null, right? Definitely it's false, right? It's not going to be true. So even if it's not base condition or anything, it's never going to be true. That's one thing. Now let's do this. Let's use recursion in the depth first manner. So always recursion is basically we can use the recursion in multiple ways, but generally like in general terms, basically whenever we talk about the depth first, we use the recursion basically, right? And again, like this is just a very generalized term, but again we can just use recursion in multiple approaches. We can use recursion in breadth first, we can use recursion in other data structure as well, but in if I have to generalize the depth first, it is recursion is the good application or the good use case to have the depth first strategy. Alright, so let's do this. Root dot left, we will go left side, and then similarly we will go to the right side as well. So because here the little bit easier thing is we have been given the sum, right? So and in another word, like if I just keep reducing each node value minus from the sum, then in the end if I my total that sum, if it equals to 0, then I can say okay, it is accumulating in a basically it is the true case, right? It is adding up to the sum, right? So what I mean to say here, let's say 22 minus 2, and that is 20, and then 20 minus I'm just following this path basically, just an FYI, right? So 20 minus 11, that is 9 here, and then 9 minus 4 is 5, and then 5 minus 5 is 0. So it is the same way, right? Either we can keep adding all these nodes, or we can just keep subtracting each node value from the given sum, and then in the end we should get 0, right? Once we get 0, we can say okay, this is the true case. I mean, we should return true. So similarly we can do this as well. It's not, I think it's not that much complicated to think that way. So either we can sum or we can just reduce each node value, and in the end we can check, okay, if it is equals to sum. So here what we can do, if our sum equals to 0, so here just be careful. So here root dot left, right? So let's go to again here and let's check here. So when we say root dot left, what does that mean? So if I navigate to the this page is fine, I think. So if I do control Z here, so root dot left so root dot left is 5 and 5 left is 4, right? So what I'm doing, I am telling my recursion that just pass 4 here and just sum minus root dot value, right? So sum initially that is 22, let's say, okay, and I'm doing 22 minus 5 here, and I'm passing my recursion 4. Then again my control in will be coming to the 4, and I will be passing left, and that is 11. So what I will be doing, 22 minus 5 is 18 here, right? So 18 minus 11, 18 minus 4, right? So I will be passing 11, but I am reducing 4, right? So 18 minus 4, that is 14, right? Now what I will do, I will pass 7, but I will be reducing by 11, right? So 14 minus 11, and that is 7. 14 minus 11, that is 3, not 7, right? So that is 3, right? So now basically here 7 left and right, they both are null. So what I should do, I should do 3 minus 7 here, right? That's what I need to do, and that's what I need to handle. So once I check this sum equals to 0, so this thing I need to check, like sum minus root dot val equals to 0, right? So if we see here, sum is basically in this case is 3, right? And minus root dot val is 7, because 7 left and right is null, right? So 3 minus 7, and that is minus 4, that should be 0, right? So that's how we should check. Basically that's what I am just explaining the flow. So if this is 0 and this root dot left equals to null and root dot right equals to null. So here the important observation here is basically whenever we are passing child root dot left or root dot right, we are subtracting the current node value but not the child value, right? So this is very important observation, and that's why I just walked through this example. So we are at 5 and we are just passing 4, but we are subtracting 5 value but not 4 value, right? Again we are at 4, we are subtracting 4 value, and then we are passing our recursive method to 11. So we are always passing the child, however we are subtracting the current node value. So that's how we are doing. Similarly to the leaf node, we are subtracting 11, and that's how we got 3 here, and we are passing our recursive method as a 7. So we should check that 3 minus 7, is that equal to 0 or not, right? That's what we need to check. And if not, then what it will do, it will recurse back and it will explore the right child, right? So that's what it should do. It will just go to the left, and then it's basically it will check, okay, root is null, means root dot left, root dot right is that is null, but this does not meet this condition, right? So sum minus root is not equals to 0. So once this is null, right, root dot left, root dot right, for both it is null, then it will recurse back and it will come to this line number 18, and it will just go to the root dot right. So what it will do, it will just explore the right part. So basically what it will do, uh, so 5, let's do the calculation here again. I think this should be the 17, not 18, right? So I did the wrong calculation earlier. So 22 minus 5 is 17, and then 17 minus 4 is 13 here, and 13 minus 11, that should be 2, and 2 minus 5, it should be minus 5. So it will come as a 2, and then basically 2 minus 2, if we will explore the right side, then it should become to 0, right? That's what it will do. All right, so that's the idea. Now once it comes to this condition, means for the 2, basically root dot left, root dot right is null, and sum minus root dot val is also 0, then what we will do, we will go ahead and return true. So that should be the idea, basic idea. And let's quickly check the complexity as well. So time complexity should be the order of n, because in the worst case, this is the binary tree. In the worst case, we have to traverse each and every node. Space complexity, in the worst case, I will say that upper bound will be the order of n. Let's assume that it is a flattened tree as a linked list, right? Then we have to uh, traverse each and every basically node, right? So in the worst case, it will be the order of n as well. Let's quickly check for the compilation error. So there is missing something. Okay, that makes sense. So what we need to do, we need to return. So we can return this guy as well. And what we can do here, we can use or. So why we have to use or here? Just remember that whenever it is not able to find any, so in this case, right, so 7 is not valid, right? This path is not valid, so this path is not valid. Then we need to recurse back, and let me choose the different color real quick here. So now we need to assume, we need to take this path, right, different path on the right side, and that's why we need to use or. End condition will restrict us for using only one condition, but for oring we have the liberty. Okay, this is the false, so this path is giving me the false. Then basically what it will check, in case of false, it will just check the other path as well to make it true. So oring is basically, if it is false, right, then if I am doing oring, it will check this condition as well. So if it is false or true, right, let's say if it is true, then the end result will be true, right? That's why we are checking oring here. And if it is ending and one is false, then it's not going to check second half of the condition, right? So we don't want that condition. That's why we don't want to use the ending here, right? So we want to explore the right side as well. That's why we are checking here the oring. All right, so let's check this. I mean, there is another mistake here. There is no semicolon. This ideally should work. Okay, now let's check for other case as well, like for example 20. These are the three test cases we have seen so far, so let's quickly run those as well. 20, and then let's see, this is false. Very good. Let's say 23 as well. And if it works, then probably we can just go ahead and let's try to submit this one if it is working. So looks like this is working as expected. So this is a fairly straightforward problem. It's not too much tricky or anything, but just wanted to make sure that I'm explaining each and every step involved in this. And don't worry about the code. This is like couple lines of the code. Anyways, GitHub repository will be there to for the code as well. But just I would recommend to focus on the concept, basically how we are doing this depth first search, how we are using the recursion, and then important topic here is these observations. So one observation is route to leaf path, and that will be determining the depth first strategy, and that will prompt us to use the recursion. And another is the all node sum is 22. So here we are just doing the subtraction, and it is little easier because we have been given this sum, right? So we can use this sum basically to reduce by each node, and then in the end we can say, oh okay, if we get the 0, then it means basically this is the true case, we should return true, right? Because there is a possibility that we have this path, right? We got this path because sum is equals to 0, right? So that's why we are doing here sum minus root dot val. And every time there is another important observation here is whenever we are just on 5, we are reducing by 5, but we are just sending our recursion method to the 4. So we are passing the child, however we are reducing the current value, and that's why we are checking here sum minus root dot val equals 0, right? So I hope this is useful. Thanks a lot. Have a good one. Bye.